Okay, hello everyone. Good to see everyone online. Hopefully everything is going well with you. This is our 23rd C++ Meetup here in San Diego, California. Weather is pretty okay compared to what I'm hearing in the rest of the nation, so things look good here. This is our couple hours where we set things aside and try to focus on having fun with C++, trying to learn new things, and basically we have a kind of a well-formed agenda. It's a bit different today. I'll explain what different in a second. A few things. First, it is sponsored by Qualcomm wireless research software, which I'm part of in San Diego. The meetup fees are paid by Qualcomm WRD software, so thank you, Qualcomm, for sponsoring that. This is my regular slide of the agenda. So first of all, I need you if you would like to have a talk. It can be any length on anything on C++ in any level. Just pick something and I'm here to help. There's gazillion, millions, billions of resources out there from video recording from conferences and all to give us some ideas of what we can bring up to the group. And yeah, so feel free to approach me if you have anything in mind that you'd like to talk in the upcoming ones. I do actually have a plan for April, so 2 months from now. JFrog would be having a talk here in our meetup. They'll talk about Conan, which I'm a big fan of. So fortunately, we would have them scheduled in a couple months. So I'll announce it when we arrive to this moment. And but anything else that you have in mind, please approach me. I'll be more than happy to accommodate requests and talks and all. So beside the welcome slides that I have right now, and by the way, there is no way I can tell who's, if you have any question at all and you using the chat, I have no way to look at it unless I'm swapping between the slides. You see my slide, right? Just make sure that.
I don't see anything.
Don't see anything. This is pretty new.
I see it.
I can see it.
Ah, you can see it, but not anymore because people said that they can't see it. Can you see it?
Yes.
Okay.
Yeah, it's visible.
Yes. I don't know. Maybe because I'm using browser.
Ah, okay. Yeah, I'm not liable to any technical issues on browser. It barely works on Teams. so yeah, sorry about it.
I'm using browser and I have no issue.
Okay.
Weird. I would try to use Firefox.
Okay, sorry about it. Usually beside the regular welcome slide, I have more things before we go to the main course. But today, since this badge of honor, this C++ 114017 slide deck that I prepared, this is part 3, and I wanna complete that. I kind of trimmed down all the other topics which are usually interesting and just left that's just the algorithm because I'm a big fan of kind of promoting that. And again, I'm saying that every time. I'm kind of inspired from Connor Orchestra, which I definitely encourage people to watch his recording from many many conferences, CPP Now and CPP Con, and he has a channel. So I this is something that I still keeping as an item. So we'll go through this just quickly, and then we'll go to the main course. And again, this definitely is something that I would like to have conversation. So stop me if you have any question, and just ask anything. Not sure I'll have answer for everything that you ask, but I'll definitely other people can chime in. Okay, we have a Dropbox link. Hopefully people can access the Dropbox link. The meetup.com header of our meetup has all the information. We have a Slack channel, which is kind of used. Actually, JFrog reached me out through the Slack channel. We have a YouTube channel that I uploading, and I'm not really editing anything. I'm just uploading as is to the YouTube channel. So you can watch the recording. Unfortunately, I just started doing all this recording and uploading to YouTube just maybe 6+ months ago. So we don't have the entire couple of years on YouTube, but we have at least the last few sessions. I have a Twitter handle, a Twitter account, both myself, Kobe_CA, and also the SDCPP meetup handle, which I manage. And let's jump to. By the way, any question so far? No. Okay, good. But please let me know if you do. So let's jump to. And I'm kind of randomly picking something that worth kind of discussing or just showing something that I solved, but homework, you can go back and try to solve it better and come back later and say, hey, Kobe, I managed to do it differently and all. There's like always few ways to solve an algorithm. Just bringing up some option. Just very simple counting vowels. This is taken from one of the websites that I'm watching, and as usual, I'm uploading everything, all the code to my GitHub account. So my github.com CA. By the way, CA is not California. It's just my initial of my last name, but it just happened to be like California. But it's just my initials, my last name initial, that is. And so you can take a look at that. You can git clone it and play with it as needed. So I'm actually going to show 3 different languages, just because I like languages. I don't know a lot of languages, but I just trying to learn as I go. So I'll show C++ first, and I'll show 2 options that I came up with. One with just the conventional algorithms, and the second one would be using ranges v3. As I mentioned, I'm using ranges v3 through Conan to bring the library into my workspace, and I have the slides that explains how to bring in Conan to your workspace. And then I'll show Rust and a couple of Python solutions just for fun. Okay, so let's say you have a word, we want to count the vowels. So let's go through the C++. So there are two solutions here. One with just conventional. One second. Conventional C++ algorithms, and the second one is with ranges. Again, I don't know if that's the most efficient one, but that's one thing that I came up with, and I'll explain it in a second. So let's say there is a string of hello world, and I have a vector of vowels, and I want to count how many vowels we have. So first of all, I just created just a simple lambda. So if you're new to C++ 11 and above, lambda is basically just a callable object, and just like any callable object, you have the body of the function you have parameters to the function, and this funky syntax where we capture all kinds of variables or elements from outside, since they are being used inside. But if you just discount this, if you ignore this, it's basically just a simple callable object where you have the body here and you have the parameters. Now this auto is basically creates like in the guts of the compiler. And I mentioned CPP Insight as a good website to see what exactly happening in the guts of the compiler. So this would be a template. I'm just out of just laziness of just creating auto. This can be a char, but auto just create a template, and I just want to mention that for people that that this looks new to them. And then there is this function that I actually didn't include here in the snippet of code, but I'll show it later. In basically, it's a very simple function, and I'll show it in a second, that returns true if a character is like if C is in chars. So it just returns true. So this function is returning Boolean. And because this is a function that returns booleans, I'll show it in a second. And this function, this lambda, is implicitly returning bool. So I'm not explicitly saying this is returning bool. This is the compiler would figure it out. Compiler usually is much more smarter than us, and the compiler would figure it out. And I'm just plug it here in a stud algorithm named count-if. And I'm passing. So basically, if you are new to stud algorithms, you usually kind of forget about this. Sometimes you'll see another parameter that has related to a parallel algorithm. But if you discount that and just take a look at the pre-C++17 ones, you'll see that it's usually a range, a begin and an end, and this C stands for const. So I'm basically not changing anything, so I'm passing const. So the input is our stud string. So C begin and C end basically are iterators to the begin and to the end. And just remember, in C++ and other languages, the end would be the one past the last element. Okay, just remember that. And then I'm passing a predicate, which is this lambda, which is callable object. So what happened is that this count-if would return me the number of how many successful true we had here. So if we iterate to hello world, every time there is a hasval returns true, we would have plus plus, and then it would I'll stud clog it and be done with it. So that's the C++. And I promise this is in, which I didn't put here. So let me switch for a second. 1 second. Let me do it quickly. Okay. So I am sharing the GitHub, and this is the main CPP, and here's this is in. And again, this I could fold this whole thing into this part. Hopefully you see my screen. Let me just make it bigger. But I just want to show just another way I could use this is in other places where I have a specific container and an element, and I'm using stud any of. So any of this, if any of these vowels match the element that I have, so that means that I'm good. And again, there's multiple ways to solve it. Just want to show an example where I utilize another stud algorithm here. Okay, so let's go back to the other option, and you can git clone it, by the way, and play with it. Okay, so so the next thing would be I would like to talk about this ranges. By the way, if I have the laser, do you see the laser?
I do.
Yes.
Yes. Okay. So so this actually I was surprised, but maybe someone can come up with something else. I didn't spend like a lot of time researching, but I actually wanted something very simple where I can count, but I couldn't find something in ranges v3 that was easier. So then this actually, if you find something that has count if similar like to count if, let me know. So what I did is I took stud filter, sorry, ranges views filter, and passed this has val. So I kind of reuse the same predicate, and this basically this would give me a range, okay, of all the things that pass. And then I could, so I take the input, pipe it into this, and I get a range. And then I can run distance on this, and I'll get the number of items. So if I see, so hello world would have EOO, so I have 3 here. So the distance would be 3. Again, if you find a different solution, please share with us either through Slack or different means. Be more than happy to look at it. Okay, so that's the C++ one, but I promised 2 other languages. So the Rust one was relatively simple to figure it out. I have this string. I'm creating an iterator. That char would give me an iterator, and then I have the dot filter, and this is basically a closure. Okay, and Rust has this pattern match, which is really nice. Once you get used to it, it's really hard to not use it. So for each characters, I'm matching either A, E, I, O, or U, and then true or false. So if it's one of them, true, otherwise I don't care, it's false. And then I'm counting the number of true, and basically that's about it. So very elegant, simple solution, which I really liked in Rust. By the way, while working with Rust, kind of a side learning exercise for me. I find Rust to be very easy to use when I want to play with algorithms. So that's one thing. So I have two examples for Python. This was like the first example, which is really not the most ideal solution, but it works. So I have this vowels, and I have this input string, and I'm using list comprehension to get a list of all the vowels. And then I have len of this. Not the best solution. I'm creating I need to create this whole list using list comprehension. It's not a generator. It's not an iterator. It's just a full list that I'm generating. So I thought about something that might work better, and I came up with this kind of a more functional programming approach where I have this filter. If you remember the Rust one, the filter is so you get this lambda at the input, and I'm basically getting an iterator. So it's basically lazy evaluation at that point. And then what I do is I call this sum function, and it would sum all the elements here, and I'll get 3 because this is hello world has 3 vowels. I think much more. I didn't benchmark it, but I think this would be a much more it's like a nicer solution in terms of performance and all. Last thing that I want to mention, a couple things. First, I highly recommend the booklet of ranges v3 that I keep mentioning this every time I'm using ranges v3 from WalletFox. So there is a link, or if you just Google for ranges v3 WalletFox, you'll get the the link. Highly recommend. The graphics and the presentation inside this reference guide is awesome, like really awesome. So that's one thing. The second thing, I have my regular slide about how I managed to get Conan working. It's super easy. I'm basically all for package management, especially if you work with Python, pip, or other package managers, and Rust, Cargo. Package management is something that I really like. So that's something that you can keep in mind. Okay, so that would be the first thing. Usually I have much more. Usually it's another 30 minutes or so. So I'll switch to the main course. Give me a sec. Let's switch slides. Okay. So if you are new to C++ 11, and the way I call it modern C++, so C++ 11 and 14 modern C++, 17 would be, I don't know, super modern. C++ 20 would be super duper modern, and so on and so forth. You can add more and more modern qualifiers as we go through the standards. This would be a nice deck for you to go through. I kind of try to get all the essential elements of the modern C++ into a single slide deck, and just one slide on each element of the newer standard or newer part of the language. And we already done 2 sessions because it's a very kind of big deck. And last time I asked if you wanted me to finalize it, and people said yes, that's a good it's a good reference and a refresher, and we do want to finalize it. So this hopefully would be the third part. It is beginners to intermediate, so I'm sorry if you are very experienced in C++. It might be a bit boring because you know all of this stuff, but if you are a beginner or intermediate, I think this would be a very interesting summary of all the options out there. So what I did, I had this idea. By the way, this slide that goes all the way to August last year, while I was in vacation with my family. Yeah, that's what I do on vacation with family. I'm thinking about how to get ideas for the meetup. So I had this idea where I'm kind of taking each feature is in modern C++ and kind of assigning it badges. Like, is it a good feature for portability? Is it a good feature for, is it gonna have a speed implication? Is it better from maintainability, safety, readability, and so on and so forth? And I try to do my best to kind of assign these badges. And basically, we went through a lot of this stuff, and I'm gonna just flip over all the way. So this is what we did on the first part. So we talked about no except, strongly type enums, stud initializer list, range-based for loop, null pointer, and which is a type of null pointer, which null pointer T is the type. We talked about auto, final class, and final function. By the way, there's a great article from Arthur D, which I can't remember how to pronounce his last name. And if you want to read about how final might help the compiler devisualize some of the use cases, this is why I kind of advocating during code reviews and all to use final as much as possible if you're trying to convey this, oh, this is a final class, or this is a final virtual function. It actually helps the compiler to deduce some of the things. Override, which again, there is a good article about how override helps to find bugs where you think you're overriding a function and you don't. So there's a lot of things happening in the past week with all of these features. Explicit constructors, const member function, which is basically not a new thing, but I like const everywhere. This is by the way, this is why I like how Rust took the const as a default. Using declaration, and so this was the first part. So I'm going to flip through the second part. This is the second session. We talked about equal default and equal delete. We just in one slide, obviously, I can't really elaborate more. It takes a whole new session to talk about the newer algorithms, including parallel algorithms. I explained about lambda, variant, optional, constexpr, chrono, which is, by the way, my favorite library in C++, in modern C++, variadic templates, tuple or tuple, depends how you pronounce it, decal type, and logguards. The whole RAII basically is a very important element in C++, and logguard actually goes under this umbrella. So, so first of all, is there any question? No, okay. So I'll continue. And yeah, please stop me because I don't see the chat or I don't see anything else. So let me know. Okay. So so stud array. So stud array is basically just a C array. But it comes with a lot of perks. It has an iterator. It has all the container interface that you are familiar with, like .size and .data. So it has a lot of advantages. One of the things that is really cool compared to a C array is that you can actually copy this by value if you want to. Like, it makes a copy if you want to, because if you know how C array works, they decay to pointers, and sometimes you don't want to decay to pointer, but you want to make a copy. So that gives you this option. It has all this .at that makes sure that you don't access beyond boundaries, with some penalty in runtime, some small penalty, but sometimes it is something that you want to do. There is a nice article from, again, author D, and what talks about, do we need stud array now that we have stud size, and so on and so forth in C++ 20. So there in C++ 20, there's all kinds of newer functions, non-member function that provides functionality that might kind of deprecate stud array with, of course, some disclaimer, like you still, if you want to pass by value, you want to use stud array, not C array. But there's some good.
I have a question.
Sure.
So is there any specific instance where you can show me why array is better than a vector when we are developing a C++ code? Why should we use an array? A very specific instance.
Okay, it's a very good question. So I would start saying that usually stud vector is your #1 go-to container in C++. Why? It's a cache friendly. It has contiguous memory, but that's why it's a cache friendly one. And you definitely want to start with it. But in some cases, you know for sure that you have this amount of data, and you don't need the heap allocation part that std_vector has. Then you definitely don't want to use std_vector. You want to use std_array. But that's again, usually when you don't know how many elements and all, you'll go with std_vector. And std_vector is really simple. Like if you're writing C and you need to come up with something like std_vector, like you have a memory that you malloc, and then you can add stuff, and then when you are done, like you're exhausting your memory, you realloc, copy everything from the old memory to the new memory and start adding. This would be std_vector. And std_array doesn't have any heap allocation. It's an what we call automatic variable. Let's say it's on the stack. I don't like this word on the stack because it can be part of a class or a struct that is heap allocated. So I don't like this, but an automatic is more, I think, more suitable. Did it answer your question?
Yep. Yeah,
Okay.
So
Thanks. It's a good question. It's a good question. You're definitely, unless you have a very good reason to use std_map or std_set or any other containers, your go-to would be std_vector. It would be usually much faster, even if you need some std_map-like behavior that you implement. Sometimes it might be faster with std_vector because it's really simple. So I have these badges. It's portability, productivity, and usability.
So
it's
I
easier
have
to maintain.
one question.
Yeah.
So the reason why we would use standard array in the place of just an array definition, and as you said, it doesn't decay to a pointer. So that is that the only reason why we would, or is there?
Well, it has a container-like functions like begin and end, for example, like for iterator. It has the dot size. It has the dot at. If you want, let's say you want to make sure that your access, this is a random access iterator, right? So you can have array, and then inside the square brackets you can say 7, and you want to make sure that it's not going beyond. So that instead of square brackets you do that at, you'll get an error. Basically, it would throw if you try to access beyond that.
Okay.
But there one of the issues with std_array is that you need to have the actual number of elements here, which is a pain. There is stud_to_array that I can take this 1, 2, 3 and just not saying, oh, it's a 3 elements. But stud_to_array is a C++20 if I'm not mistaken. So it's kind of a trade-off. I use std_array instead of the CRA. In terms of runtime, if you're not using the .at, it's going to be compiled to exactly CRA. So
Okay.
there is it just has all kinds of functionality that are inline and templated, so it goes away, which you don't have it in a plain CRA.
Okay. Thank you.
You're welcome. So in C++11, we got a new container named forward list, and forward list is basically fills the gap of, instead of having doubly linked list, which is std list, is let's say we just need a forward list. We just need a forward iterator. We don't need to go back. So why pay another
Yeah, one
pointer?
question.
Yeah.
Like you in list, right? We have the list. List is based on your double-ended double linked list, right? But most of the functions of forward list can be performed with the list. So why do we? I've hardly come across any case where forward list will be very useful than the list.
To be honest, I barely using list. I don't remember the last time I used list. So
Yeah, so like in a lead code, right? There's a very famous problem called LRU cache, right? We usually in LRU cache we use a double linked list, right? So we rather use a list in that.
Yes, If you need a double linked list, you can use list. This is basically there. I don't know if I can find you right now some use case like from real world, but it definitely if you don't need to pay for the back pointer, just use forward list. It's just there for you in the tool set, just in the toolbox. Just use it when you don't need to pay the reverse. Like basically you reduce the footprint of your memory, right?
Right.
It's just an option. I'm not saying use this all the time. That's not my intention. Just I'm introducing something new in C++ 11 that can be useful in some of the cases. In C++ 17, there was a new syntax named structured binding that a lot of languages already has, like Rust would have it, and Python would have something similar, and so on and so forth. The nice part of it is that I can take a specific structure. It can be a pair or a tuple or whatever, or a struct, and I can deconstruct it into the elements. And this became super useful in many cases, in many use cases. For example, let's say we have a map here. I'm just populating the map with two elements, 1, 2, and 3, 4. And let's say I want to iterate over the map. So I'm using this new C++ 11 range for loop. So I have this for. This is the container that I'm iterating. I have this colon between what I'm iterating and what I'm extracting every single for loop iteration. And what we see here is that the nice thing is that I am actually getting this key value. And if you're using Python and similar, it should ring a bell because this is very similar. So before that, what we used to have is a pair, and you'll do like this. Let's say the pair name, the variable name p. So p dot first, p dot second. It was very cumbersome. Key v or kv or key value is much more readable. So this is why it's really readable. It's much safer in some cases where I'm getting the exact thing that I want. Easier to maintain, and it's basically makes it much more usable. You can see that I don't have the alternative, but you can imagine that I have like this stud pair of int, and I need to use dot first or dot second, which is kind of cumbersome. There is no name for that. It's kind of not so readable. Another thing in C++ 17 that might be useful is that both in if and in switch, if you have something that you want to initialize that is only for this block, and you want to reduce the scope instead of having this var equal 10 defined before the if and then use it inside, you can actually define it here, have this summacle, and then you have the regular if condition. And this var has the scope of this if else. There is no else in this case, but think about this if else. This is very useful if you want to reduce the scope of a specific variable, and we have the same for switch case. I found it very useful to reduce scope. I really like. There's a lot of people advocating to reduce the scope of your variables as much as possible. So this is one way to do this. Some people find it confusing because they're not really used to the new syntax. So they say it's less readable because it's really new. I found it very useful. And remember that reducing scope is a good thing. One of the best practices is reducing scope of your variables. Inline variables is something that I provided a session, like a 45 minutes some time back. I don't remember if I have it recorded, but long time ago, before C++ 11, actually C++ 17, we couldn't, if we wanted to have a variable in the struct or in the class, I needed to actually also define it in a CPP translation unit in order to linker to be happy. This is gone. We can say, okay, this value, a static one, is inline, and the compiler would not require it to be like doesn't need to have it defined in the CPP outside of the class. Makes it very easy, especially for header-only libraries where they don't want any CPP. So lib authors of header-only, they make heavy use of this. It makes productivity and all implementability much easier. You don't have another place where you actually define all comes in the same line. So makes it very useful. It's kind of a niche if you don't need it, but when you actually need it, it comes to be very handy. CPAPA 17 gave us a nice new type called stud_byte. And stud_byte gives us a way to access just a raw buffer. So this is kind of intent. And if you download my slides, I have in the notes of this specific slide, there are links to Stack Overflow and other links to that explains in details why it is much better to use stud_byte than, let's say, uint8. And in a nutshell, stud_byte tells the reader, look, there is nothing here just beyond a raw buffer. So it's not so every time I look at a specific chunk, there is no sign or unsigned. It's not an integral. It's nothing. It only defines bitwise operation. That's it, which makes it much safer because I'm kind of communicating intent that I just want a buffer and I just want maybe have all kinds of bitwise operation, but I don't have any mathematical operations on it. So I'm not going to make any mathematical operations on like if you have a uint32 or uint8 and all, people might be mistakenly think, oh, I can make all kinds of arithmetic operations, but with stud_byte, you kind of constrain that as needed. So it's pretty useful. One of the things that as you use it more and more, it's verbose when you start understand you understand that C++ standard had a lot of things done. A lot of the defaults were done incorrectly. For example, the no discard one is an example. We already talked about explicit constructors. No discard is one of the things. So if I write a function that returns a value, and I really want to make sure people look at the return value and do not ignore it by mistake, I'll slap this no discard attribute. And C++ 11 and beyond define a lot of attributes, and it's getting, I think things are getting more and more attributes as we go. And this is one of them, which is super useful. I use it everywhere in my code that I want to communicate. And usually if I return a value, I want it to be looked at. And sometimes it is okay to kind of ignore the value, and then you can static cast to void, and that would silence the compiler. But if you don't, the compiler would give you a warning /error, and you basically cannot kind of avoid it. And also, all kinds of static analyzers can help you figure out, okay, this is something that you need to look at, and you're making mistakes that you're not. So I highly recommend using it as much as possible in your interfaces. One of the things that again, it's you'll see it more for if you're writing interfaces for others, you're writing templates, you're writing template meta programming, which is kind of a more advanced topic in C++. Sometimes you want to check stuff in compile time. When I say stuff, there are two things that you can check. One, you can check types. You can query all kinds of traits or questions on this. Hey, is this type an integral? Is this type a floating point? Hey, is this type I don't know, a base class of this class? Like is this class derived from this class? All kinds of stuff that you can actually query during compile. This is whole compile time, and then you can assert, hey, I actually list this. For example, here's an example. I'm writing this template class of T, and I want to make sure that people, like when I say T, everything can be instantiated here, right? And then things might compile or might not compile. It depends on the implementation of class foo. But I can actually put a static assert if I want T to be a type of integral, like uint8 or int8 or 32 or 64 and so on and so forth. But I don't want people to pass me a double or a float. Then I can static assert it. And this is integral is coming from the standard library type traits. And I can have this message, oh, this is not integral, and the compilation would stop. In C++20, there is a new thing named concept. I'm not showing it here in the slide deck, but just be aware that there is something named concept where you can improve the way you kind of create messages to the user that there is some restrictions on a specific type and so on and so forth. But this is definitely good enough for you if you're using all the way to C++17, even beyond that. Okay, if you care about all kinds of alignment and how the layout of your variables and data looks like, C++11 added something called align as. And here's an example that I took from CPP-Ref. And I personally use it in a couple places in my day job when I need something to be aligned to a specific alignment. So this is portable. Instead of having all kinds of compiler intrinsics or something like that, this is a portable approach now that works across all C++11 and above and beyond compliant compilers. So let's say I want something to fit into a 256, exactly 256 alignments, because I want to do some SSE stuff, like there are 4 floats here. So this would be the way to do it. This is an example of SIMD, but there are other things that would work perfectly if you're getting something from the network and you want to copy it to something that is aligned to specific alignment. Align as is your friend. You can define struct, you can define variables with align as. Very useful. Kind of more on the advanced part, but definitely useful if you need it in your code. So C++17 added something named string view, and string view is basically just like other similar and other languages. For example, Rust has something similar, and other languages has something similar. It's a kind of a lightweight vehicle to have a view on a string. So sometimes you don't want to pass maybe your strings, stud string that is, around. You just want to pass a pointer and a length. And what C++17 provides us is this stud string view that I can actually construct a std string. So this is how I constructed this S here is with the using name. I don't have this using namespace because of space, but this S means this str is it's a std string, and I can call this function. And this, what happened here is that S would have a pointer and a length. So it would have a pointer to hello world and the length of a hello world, and then I can do some stuff. And this is very, very, very useful when you have code that does a lot of string-related work. And there is this podcast named ADSP that Connor and Bryce started a few months ago, and I think in the second or the third session, Bryce mentioned that this string view helped a lot in some of the algorithms that was heavy on string processing. So this is a great thing. Just remember, C++ doesn't help you to make sure that this string view points to some memory, right? This memory needs to be alive as long as the string view is alive. Like this hello world need to outlive this string view. In other languages like Rust, there's mechanism in the compiler during compile that checks all of this. We don't have it in C++, so you need to be aware that, and this is even if you are in C, it's the same thing. If you are in C and you have something that looks like std string and you want just to have another struct that has a pointer and a length, you need to make sure that this pointer and a length, they point to some valid memory that outlive your struct that is viewed to this string. So nothing really, especially you just want to mention, just remember that this is something that there's a lot of pitfalls that I'm seeing around. Just remember, it's just a pointer and a length. It doesn't know about null terminated and all. So if it points to something that has a null terminated, that's fine. But let's say you have a string of 100 characters, and you create a std string view of the beginning of the string and a 50. Okay, so just remember that it's just a half of the string. There is no null terminated after this 50, right? Because it's just a pointer and a length. I see it a lot, like people kind of complaining, hey, I'm holding a string view of a pointer and a length, but it's not null terminated. Like, that's not the point of string view. String view is not like, oh, I'm gonna change the string that I'm pointing to. No, I'm just wanna have a lightweight view, which is just a character pointer and a integer that tells me how much I wanna have, and I wanna make some processing on this area of memory, and that's it. Just remember this, because I already heard a lot of, in my career, a lot of people kind of bitching about, oh, string view doesn't work for me and all. It's actually a very good it's a very good thing to use if you know how to use it properly. There's a lot of smart pointers, there's 2 of them. There's a lot of use cases to use them. The kind of a rule of thumb is don't use row, new and delete. Just use make unique, like unique point. Make unique, basically create a unique pointer, which is basically just a pointer wrapper. But it has this nice feature of RAII. So every time you hear RAII, it's basically, in other words, it's a class or a struct that manage its own resources. So how do you manage your resources in C++? If you have an interview question, it's easy. Your constructor might allocate the resources, and your destructor, which is called at the end of the scope or when you delete the object, depends if this object was newed. So the destructor would be invoked when the object dies, and then the destructor has the opportunity to clean the resources. So when you hear the term RAII, it's basically fancy word to say, okay,
Yeah,
this is.
the thing is, even in smart pointers, we might have some limitation, even though it's a, I mean, limited garbage collection utility. So like a cyclic dependencies or a reference cycling is a major problem in smart pointers, right?
Yeah. Let me
So it's
address
not
that.
100% a pure solution for this.
Yeah, let me address this. So usually in unique pointer, not usually in unique pointer, there is only one owner. You can still pass the pointer. There is a way to extract the pointer, the dot get. You can still pass it, and there's a lot of good, by the way, recording from Herb Sader about how properly use unique pointer. You can still pass the pointer around, but there is only one owner. Okay, now shared pointer is a different thing. First of all, I'm using shared pointer very, very lightly, if any. It's basically, when you use it a lot, it's like global. People start using it as a global, and you can read online. I've seen it happening where some people say, okay, shared pointer is actually it's the C++ garbage collection, so I'm going to use it everywhere. And this is where the cyclic dependencies that someone here mentioned kicks in, and then you need to use like weak pointer, and it becomes very cumbersome. Use shared pointer in a very, very specific use cases where, and I can give you an example that I've seen at least once. Use it just when you really don't have an owner. Okay, so here's an example. Let's say you have a queue between a producer and consumers. Okay, uh, uh, so let's say you have a producer that creates a shared pointer, put it inside a queue, and then consumers are actually consuming that. And only when the last one is done, you want this resource that was allocated to be gone. There is no actually one owner, right? Because there are multiple consumers that actually consuming it. So that's one example where you really don't have a single owner. But I actually I tend to see a lot of in code reviews and code bases, a lot of misuse and abuse of shared pointers, and big people like Sean Parent and all uh, can basically you can go and read their opinion that people actually misuse it a lot and actually abuse it. So don't use it liberally. Don't like use it everywhere. It's not good. Use it only, and then weak pointer and all comes into the picture where you just want a view which is not participating in the counting, but it keeps the shared pointer alive. This is whole this whole cycle dependencies that someone mentioned here, which is a big issue when you start using shared pointer all over the place. Don't, please don't, because it's really hard to maintain.
All right, I have a question, Kobe. So, hello?
Yeah, I can hear you.
Yeah, so for the unique, so basically when you create the unique pointer, then when you're passing to the others, so you're still passing the original raw pointer, right? Is that how the usage looks like?
Okay, this is actually a good question, and unfortunately, it's actually a good topic maybe to present, because there are guidelines how to do that, and it goes back to your question. So I'll give you an example. Let's say you have an interface. You created the unique pointer, and you have an interface that you interfacing with. Like you have a function. This function has a unique pointer as a parameter, and you want to pass this unique pointer. So basically, when I have a unique pointer, by the way, by value, when I have a unique pointer in my interface, what I'm saying here is that I want to consume a unique pointer that is passed to me, to my function. I'm the new owner. Okay. If you have an API that you can trust, by the way, you can trust, like API that you you have a unique pointer, and the API has a pointer, and you pass the dot get to you pass what you telling this like to the reader is that, look, I'm still the owner. I'm passing this pointer to the function is going to use the pointer as much as it wants, but the function is not owning this pointer. So the function should not deallocate this pointer, for example, because it's not the owner.
Mm-hmm.
So there are a set of guidelines that people from the committee put together, and I'll try to find it because it's a good guideline, and it was the kind of I don't think they came up with the whole thing at a single point of time. I think it kind of evolved as we use it and kind of got more experience of how to use it. But Herb Sutter has at least one recording, at least from CPP Con, maybe 3, 4, 5 years ago, where he actually addressed this specific question, like how do you make a good interface using smart pointers? And he also talks about shared pointer and all. But I think there is also at least one blog or article that I read like a long time ago that I need to dig into my bookmarks and see if I can post it.
Okay, sure. Thanks.
And it's a very good question that we deal daily when we write interfaces that has smart pointers included.
Right. Normally, so I think the question is, so normally I in the class I have a container, right? I create a lot of objects. I using the make unique, right? Because container contains a unique pointer to the object. But the object eventually will go out to all the functions, the other classes to get used, right, or processed. So normally the question might, or for those classes or functions, do I define a full star or I define or using the unique pointers? I think that's the confusion I have.
So specifically for your use case, I'll say the following. If you want to pass ownership, so you can have a unique pointer by value on the interface of each of the functions.
Normally, I don't want to pass the owner. I'm still the owner.
Exactly. You usually want to retain ownership in this class that has the container with the unique pointers, right?
Right.
You want to maintain. I'm the owner. I'm just giving you the pointers. You go use it.
Yeah.
But you're not gonna deallocate it. Or you can't. I guarantee you that your pointer that I just passed you would not be invalid. My unique pointer would outlive your function. This is a promise that you need to make. If you start doing all kinds of multi-threading and you pass it to a stud thread, you need to make sure that your class that holds the stud this unique pointers doesn't go away while this thread that you pass it this pointer is still alive, right? So this is stuff that you need to manage as part of your architecture. But the point is usually you want to maintain ownership in your container.
Right.
That's usually what I do. I rarely pass the ownership, and then my container has nothing, which is just sitting there wasted because I moved the ownership to some other component, and now I have just a useless container with just null pointers, right? The unique pointer after you moved from the unique pointer would have null pointer. So usually it's not a good architecture. One of the more maybe confusing, maybe cumbersome feature, but very important one, by the way. Like it's the heart of one of the main features in the modern C++, named R-value reference or R-value references. And I have an example here. You sometimes hear the word move semantics, and in Qualcomm, I had at least a few sessions that I provided to explain what does it mean. To put it simple, before C++ 11, we only had one type of references. We had L value references. It's just the regular references that you are familiar with, which is something like this. Okay. And a reference basically inside, it's a pointer. It's kind of a synthetic sugar, but it has all kinds of advantages. For example, inside foo, I know that even though bar inside, like in the guts of bar, it's a pointer. Like I'm kind of using the terms loosely. Bar is not null because reference cannot be null. Okay, so there's all kinds of advantages to use the C++ references. But we had one problem. If I had a temporary, I couldn't pass this temporary to a function that had a reference, unless this function had the reference was a const reference. But let's say it wasn't a const reference, I couldn't have it. So one of the things that was added is that R value references, and then R value references means that I can bind this bar here to an R value. For example, in temporary. So let's say this get bar. So let's see how it would work in practice. I have two functions overloaded. In C++, we can overload the function name with a different parameters. So I have a different parameters. One is a ref, which is an R value reference. Okay. And the other one is a reference, regular reference. I have this, so these are two functions. I have another function that returns a bar, an instance of some class. And if you familiar with C++, the regular C++, not or even more than, I'm actually returning something by value. So there's going to be a copy made, like technically speaking, there might be some elision happening, but this is get bar returns me an R value. It returns me a temporary. So before C++ 11, this was the only function I could use. And if I was trying to do get foo of get bar, I would fail compilation. And the compilation would say, hey, if you want to pass a temporary to a reference, the reference needs to be const. There was a restriction that inside the function, bar is const. Why? Because it's a temporary, and the designer of the language said, if I'm inside a function and I've been passed a temporary, don't think that changes that I'm doing to this temporary would be visible outside of the function. This is a mistake because someone passed you a temporary, and this temporary would go away after the expression is gone. So to avoid such confusion, a const is mandated. A const is something that you must have in the function signature. Otherwise, it would not compile. Okay, so this function would work, right? Bar is an L value, so the compiler in compile time would bind it here. If I'm changing bar, I'm changing the bar that is outside. So there is anything I change in bar, since it's a reference, non-const reference, would be visible out when I'm done with the function, would be visible outside. Now I have this new shiny feature here in C++ 11 where I can actually pass get bar, I can pass this R value. Now, the interesting part of this whole thing is the following. When I write a function that takes an R value reference, the convention says is that I've been passed something, this is a temporary, or was cast to an R value reference because the caller of this function explicitly cast it to an R value, which means the author said, look, I don't need this element or this instance anymore. It is as if it was temporary. What does it mean? It means that I can do all kinds of stuff inside this function to this bar. I can actually take, let's say bar has a a dynamically allocated memory. I can actually use this dynamically allocated as is, as if I was the owner, because I know this, whoever passed me this temporary is not going to use it anymore. Before C++11, we would need to make copies in all kinds of use cases and scenarios. The R value references provide us a technique where if I have a temporary, I can actually pass it to someone that can take the guts, they can pull the guts of this temporary instead of making a copy, can take the guts of it and use it. So again, this is one of the more complex stuff in C++11 that was introduced. So, and I'm trying to, there is a book of, I don't know, a few hundreds of pages that just talk about R value references and std move. So I'm trying to kind of summarize it in a few minutes. So it might be a bit hard to kind of grasp if it's first time, but this is kind of a very unique way to speed up things in C++11, where you can actually make use of temporaries much more efficiently. Okay, so remember this. Which brings me to another slide, kind of similar, which is how, let's say I have an L value, how can I cast it to an R value? So std move is casting a specific L value to an R value, and then it can be passed to this function. And what I'm saying here when I writing std move, by the way, there is of course, something confusing. There is an algorithm named std move. It's an overloaded function. So std move is a function. So there's an algorithm where you give a range and another range, and you can move elements from one range to another range. This is a different thing. Here is a cast. This is std move is a cast. Std move, by the way, doesn't move anything in this example or in this overload. In this case, it is casting it to R value. And what I'm saying here is that, look, this foo that I created and maybe used it here somewhere, and I'm now calling this function, I don't need it anymore. And it's going to be a mistake, and static analyzers are very good at it, that if I'm trying to use foo after I cast it to this R value, if I'm trying to use it here, the static analyzer would tell me, hey, you're trying to use something that was casted to R value. Someone already used it and took ownership on the guts of this instance. You don't want to use it. Okay. And again, other languages like Rust, they enforce it much better as part of the compiler. The move constructor is basically everything that I just mentioned would be applicable to move constructor. So here's an example. I have this struct foo, and it has a pointer. And let's say that we allocate some pointer in this pointer, allocate memory in the constructor, and we deallocate it in the destructor. Okay, and I'm creating this foo function, foo instance, and I have this bar. And this bar, I'm passing foo by value. Before C++11, you would create a copy constructor. Let's say you allow copies. So usually what you would do, you have a copy constructor that is going to allocate the data for the copied element. And again, this is regular C++. This is not modern C++. This is what you would do and because you don't want to have a shallow copy. A shallow copy is bad, right? Because you'll end up with two instances that are pointing to the same memory. And this is bad because both of them will try to deallocate. So you want to write your own copy constructor that is doing allocation and all. So before C++11, if you needed to take a copy of something, you'll make a copy. But sometimes I don't want to make a copy. I actually want to move the ownership from this instance to a different function and let the function, look, you are the owner from now on. Okay, so there are two options to do it. One is I'm casting it to an R value, and I have an proof constructor. This is a new thing from C++11 where it takes this R value reference and still this foo is being, the pointer is being stolen and I'm assigning it to null pointer. Again, I'm trying to get a lot of information in one slide, but the bottom line here is that this makes stuff super efficient. Like I can't use foo after this line because I casted it and bar now took ownership. But there are a lot of use cases, a lot of use cases that you don't even aware, you're not probably aware of, that we're using the standard library, that move constructors actually makes your code move, work faster, because you might deal with temporaries and all, and these instances, these types have move constructor that actually just move the pointers from one instance to another one and not making any copy. You're not going to have it's not like a shallow copy that I mentioned before. It's actually because I'm assigning null pointer to the incoming one. So basically, after I created this instance and I'm calling bar with this stud move, this foo after this line would have null pointer, and the actual, when I call bar, the pointer was moved into this foo. They'll do something with it, and that's it. This foo after this bar function is kind of empty. There is no, the allocation is not, this instance is not owning any allocation. So again, this is, just remember that this is one very important C++11 element that was introduced and is very important. And again, I'm trying to have a lot of information into one slide, but just remember that it exists. So if you creating a class or creating a struct, just remember that there's all kinds of techniques. And this, let's say this struct is managing resources. There are all kinds of techniques to make your code run faster, and just go back to this slide deck and have it a reference and then start reading, or maybe ask questions, your peers and all. Just remember that this stuff exists. By the way, other languages like Rust, they have move by default. And if you want to make a copy, you need to be explicit. So some languages took it, like were designed in a different way. Like they moving ownership as a default. Stud any is a new container that can hold anything. It's using something called type erasure, and it's basically a very like a type safe void pointer. Okay, so you can query, you can have a more portable way and safer way to extract the value, versus if you were doing it in C++. Sorry, in void pointer C. It's basically, if you think about it, Python is like stud any everywhere, right? Because Python, you have some type, you assign v equal 7, it's an integer, and then v equal hello world, it's a stud string. It's like a stud any. If you want to have Python in your C++, you just use stud any everywhere. But this is of course a joke. Don't do it unless you really need a void pointer like container. Unlike stud variant that we already mentioned, stud variant can hold. It's like a union, right? It can hold up to a specific number of types. Stud any can just in runtime can just hold anything. So it's different from stud variant that has a very specific number of types that it can hold. Maybe unused is very handy if you have a, it's a combination of, oh, I have this function that has parameters or something similar, and I don't need the parameter, but my static analyzer requires me to have this parameter. Or sometimes this parameter, you have a cross-platform code, a multi-platform code that in one platform you need this parameter, in another platform you don't need this parameter. You have this way in C++, I think this was 11 or above, I can't remember exactly, has this, this is 17 actually. This is for sure 17. You can have this.
I have one question previous to, I mean, when you were telling about the any. So how's like any much different from auto? Like I can still use an auto if I don't want a specific data type or something like that.
Auto is resolved in compile time. Like in compile time, auto is not a void pointer or is not, I don't know which type it is. You might don't know when you look at the code, but the compiler knows at compile time. Stud any can be like think about stud any, a variable stud any, that I have an if something, stud any equals 7, else stud any equal hello world. Okay, let's say it's anything. Like stud, what happened here? If you look at anything can be 17 or can be hello world. So it can be two types. This is something that you don't have in compile time. In compile time, a specific variable has a single type, and that's it. Here's anything has this stud any that inside can be any type in runtime. Auto is not a runtime thing. Auto is a compile time thing. Auto is a syntactic sugar where I say, look, I'm having auto v equal 7. I want to let the compiler figure out what 7 means, and 7 is an integer. So this v would be an int. It happens in compile time.
Okay, thanks.
You're welcome. So maybe unused is a very nice thing to throw in, and the compiler would say, oh, because if you turn on all kinds of warnings and all, the compiler would say, hey, you're not using this, please use it. So maybe unused is a very handy one. It has no implication in compile, like in in runtime or anything like this. Just to silent your compiler, silent your static analyzer because of specific use case. And I used it here and there, usually in cross-platform code, or maybe when I needed to write the name of the parameter, but I didn't use it. But I still need to write the parameters because clang tidy, for example, would tell me to do so. Another thing that was introduced in 11 is string literals. This is basically a way to have anything inside this. So inside this parentheses, I can write anything without the need to escape, without need to use / something. Very, very useful if you have a very complex string that has all kinds of quotes and whatever. You just put this R, quotes, and parentheses, and inside the parentheses you can have anything, and you're done. You can even have embedded new line if you want to, or tabs, or whatever. It would be as is. So it's really, really nice. I definitely use it when I need to have this strings, and I don't want to have any escape. So I use this R. C++ 17 added few utilities, functions that helps us to convert to characters and from character. So all this str to L and similar or iota and sorry, I2A, not iota, but I2A and similar. This is a new standard that has a much better performance and better error reporting that I'm using in my code. So take a look at there's nothing, you probably use string to integer or integer to string conversion. This is a very handy to use. The design is focused on efficiency and speed, less on functionality. So there's some functionality in the regular C functions that has a bit more stuff, but they are slower, like in benchmarks, because the standard wanted to, for this specific function, focus on speed. So these are much faster, and there are all kinds of benchmarks that you can find online regarding all kinds of compiler implementation, like standard libraries implementation in different compilers, MSVC, GCC, Clang, and so on and so forth, that shows how fast it is compared to the like the old conversion, string conversion. I have one slide on the C++ 17 file system library. It is portable with some asterisk here. There's some caveats that there is in the slide notes. There is a link to a book that has a chapter on the caveats on C++ 17. So go ahead and read it. I find it useful to make it portable and more usable and easier to maintain and easier to read. Whenever I need to use file system API, I would go and use the C++ 17 one. Some I know that some of the NDK of Android, some of the C++ implementation are not completely up to date with not 100% compliant, so they might be missing, but they'll catch up. And other platforms. It's pretty new and it takes time. Like it's not that new. It's C++ 17, but some platforms still lacking it in their standard library implementation. So I already mentioned in the static assert, so I kind of having this type traits. Type traits, I recommend you go to cppreference.com and take a look at the type traits. There's a bunch of compile time queries that you can have, and it's usually, lib authors would do that. Maybe if you're writing an API and you want to have you want to question, like you want to query, hey, is this type is what I'm expecting, or so on and so forth. You're going to use it. It's really more on the advanced part. I would be like, to be honest, this is more on the advanced part of the C++ part. So as you kind of move into the more expert part of the C++, you'll use it more and more. It's a huge productivity saver when you need it, because you can query all kinds of things in compile time, and it also helps to show what are the assumptions on all kinds of parts of the code. This is this is not as the regular assert. The regular assert that this is a runtime assert. Static assert is a compile time assert. It's not a runtime. Nothing happens here in runtime. But this whole thing goes away in runtime. It's all compile time assertions. Okay, Stud thread is a new C++ 11, kind of a portable, safer. Maybe if you're a library author, you're gonna use it. Much more readable than like using the platform stud thread. Sorry, the platform thread library. Let's say Windows has their own, and POSIX have their own. This is a more portable way. And it's not only the stud thread, it's also the concurrency element. For example, cards, like I want to have a mutex and atomics. And there are a bunch of them that you can go and look at in CPP reference. There's also async operation, package task, condition variables, locks, and C++ 20 added a bunch of other stuff like thread tokens, joining threads like JThread, all kinds of barriers and latches and semaphores and so on and so forth. If you're dealing with multi-threaded applications in C++ 11 and beyond, you need to be very fluent to take a full advantage, and you definitely want to use what C++ 11 gave you. This is a huge step forward in all the concurrency and using threads and so on and so forth. Like a very, very important thing to go and read about. C++ 17 added something named string searchers. There is this search function where you can actually run all kinds of search algorithms on a string, all kinds of sophisticated ones. There are a lot of blogs and articles about the string searchers and comparison about all kinds of the searchers that provided by the standard library and benchmarking it. But if you are dealing with all kinds of string manipulations and string searching and so on and so forth, you definitely want to take a look at the C++ 1720 searchers on strings. So very smart people, develop all kinds of algorithms to find what you're looking for in a big block of string in efficient way. So definitely take a look at this part. And this will be my last slide. This is C++ 20 span, and this is the only slide that I have on C++ 20. And the reason is that someone in the previous session said, "Hey, Kobe, do you have something about C++ 20?" And I was no, and he was like, "How about span?" And he really liked span. And basically, span is basically just like string view. Remember string view? It's just a view on a specific memory, contiguous memory. It can be a container, it can be an array, but it started with the GSL, the guidelines library, guidelines support library that you can find in GitHub, and was adopted by the committee and it added to C++ 20. It's basically a lightweight mechanism to pass pointer and a length around. Now, string view is a read-only kind of view. Span, on the other hand, is basically a read-write view. So that's one of the differences that I can highlight. It's a safer, more readable way to pass pointer and a length, but it has all this nice interface of container interface, like begin and end and size and empty and all of this. So, yeah. Someone asking something?
Yes, I think it was me that was asking you about span. And I want to
follow. Okay.
I wanted to let you know that I actually implemented span in my project, and I'm extremely happy with the results.
Okay. So thank you. So I have this slide done thanks to you. Hopefully you're happy with the slide. Yeah, it's actually it's something that a lot of people like and a lot of people use, and static analyzers would tell you, hey, please use span instead of passing, you know, just bare pointers and so on and so forth. So if you don't have C++20, you can have GSL, or you can implement span, just like someone just mentioned. You can implement span and be very happy on using it. So this, as I mentioned, this is my last slide. I'll upload the slides to our Dropbox, and feel free to ping me on any question. This is definitely how many slides we have here? We have about 52. So you have a 52 features that I collected for you that you can go and look at, and the idea is that when you need it, you go and research the whole thing in a much more thorough manner, but at least you have an idea of how things look like in the modern C++ land. Okay, so we can stop now, and unless anyone has a question, I'll be more than happy to discuss. If not, we can call it a day, and thank you for joining.
Thank you for presenting.
Yes, thank you for presenting.
No, my pleasure. I had fun. Hopefully you had fun as well. Yeah, feel free to ping me. If you're in Qualcomm, you can ping me on our MS Teams. If you're outside, we have the Slack channel, and you can, if I'm not available, you can reach me through emails, LinkedIn, anything else works for me. Thank you, everyone. Take care. Good night.
Thank you.
Thanks, Kobe.
Take care. Have a good night.
Thanks, Kobe. Have a good night.
Good night.